Okay, let's go. Number 1. The Hercules-Corona Borealis Great Wall. The year is 2014. You're a gamma-ray burst researcher at the Hungarian Academy of Sciences in Budapest. The server room runs continuously behind the wall you're facing. The air in the corridor is recycled faintly warm, carrying the metallic trace of cooling systems working at capacity. The fluorescent lighting is the same at 3 in the morning as it is at noon. Your coffee is cold. Your terminal displays a three-dimensional scatter of gamma-ray burst positions accumulated over a decade of satellite data. You know what a statistically uniform scatter looks like, not a preference, not a rough estimate. You have looked at hundreds of them. What you're looking at is not that. Istvan Horváth, John Hakila, and Zsolt Bagoli published their analysis in Astronomy and Astrophysics in 2014 paper A and A 561 L12. The dataset maps 283 confirmed gamma-ray bursts across a narrow declination band. Gamma-ray bursts are among the most energetically uniform events in the observable universe. They occur when massive stars collapse or neutron stars merge, and their brightness makes them detectable across billions of light-years. Their positions trace the three-dimensional distribution of matter in the early universe. What the Horváth team found in this particular band of sky was a statistically coherent grouping at redshift z equals 1.6 to 2.1, a range placing the sources approximately 10 billion light-years away, in a universe between 3 and 4 billion years old. The statistical significance registered at p below 0.001. A confirmation analysis appeared in monthly notices of the Royal Astronomical Society in 2015. The structure spans approximately 10 billion light-years, from edge to edge, 1/13 the diameter of the entire observable universe. The cosmological principle is not a preference held loosely. It is the mathematical foundation of the standard lambda CDM model, the framework used to describe all large-scale structure formation in the universe. The principle states that at scales above approximately 1.2 billion light-years, matter must be statistically uniform. Standard models allow for coherent structures up to roughly 400 million light-years, and producing even those requires the full 13.8 billion years the universe has existed. The Hercules-Corona Borealis Great Wall is approximately 10 billion light-years across. That is 25 times the theoretical maximum. It is 8 times larger than the scale at which the cosmological principle predicts uniformity must hold. Here's where it gets strange. The Great Wall doesn't set a new size record. It breaks the mathematical framework used to model how all structure forms. The cosmological principle is not a secondary detail of the lambda CDM model, it is the premise the model is built on. A structure 25 times the maximum permissible scale, observed when the universe was between 3 and 4 billion years old, doesn't just challenge the model. It challenges the model's right to exist in its current form. Critics have argued that gamma-ray bursts are an imprecise proxy for mass distribution, that apparent clustering could reflect uneven satellite detection efficiency rather than underlying structure. Horváth addressed these concerns across multiple follow-up papers. No dedicated observational campaign using alternative mass tracers has been funded to resolve the dispute. Not a retraction, not a refutation, an open disagreement, unresolved, between the detection and the model that cannot accommodate it. Does the grouping reflect a true mass concentration or a bias in how we detect extreme energy events? If true, what early universe process generated 10 billion light-years of coherent structure in under 4 billion years? Is the cosmological principle an accurate description of reality, or a useful approximation that fails at the largest scales? And if the foundational assumption of the standard model fails at this size, what else in the model fails with it? That structure is 10 billion light-years long. The next entry isn't defined by presence. It's defined entirely by absence. Number 2. The Boots Void. You're a radio astronomer at Kitt Peak National Observatory in Arizona, compiling a galaxy redshift survey across a section of sky that should contain, by any reasonable statistical estimate, a reasonably uniform scatter of galaxies. The observatory dome sits open above you. The night air is the particular dry cold of high-elevation desert, not the damp cold of lowlands, but a clean, thin clarity that carries sound oddly across the dark. The instruments produce a steady mechanical hum, the occasional relay click, the soft motor tracking the rotation of the sky. The desert smells of dust and cold stone at this elevation. You are cataloging. You are not expecting anything unusual. You expect galaxies. Instead, you find nothing. Robert Kirshner, Augustus Oemler Jr., Paul Schechter, and Stephen Schechtman published their findings in the Astrophysical Journal in 1981 paper, APJ 248, L 57. What the survey found was a region of sky, approximately 330 million light-years across, that contained almost no galaxies. Not a sparse region, not a thin patch. A coherent, spheroidal emptiness, stretching more than 250 million light-years in every direction from its geometric center, with the surrounding large-scale structure abruptly resuming at its edges. The contrast between the void's interior and exterior was sharper than any survey artifact could produce. The emptiness was real. The cosmological principle predicts voids. Under standard lambda CDM, regions of relative underdensity form as dark matter collapses into filaments and nodes, leaving gaps behind. The maximum void diameter the model predicts, under standard gravitational processes operating over the full age of the universe, is approximately 150 million light-years. The Boots void is 330 million light-years across, more than twice the predicted maximum. The formation timeline required to produce a void of this size through standard gravitational processes is estimated at approximately 1 trillion years. The universe is 13.8 billion years old. The ratio there is roughly 70-1. If you were positioned at the geometric center of the Boots void, your nearest neighboring galaxy would be approximately 1,000 light-years away, compared to the typical separation of a few million light-years in populated regions of space. Everything in every direction would be dark. Here's where it gets strange. The Boots void is not entirely empty. At least 60 galaxies exist within its interior, and they are not randomly distributed. They are arranged in a thin, looping filamentary structure that astronomers have informally called the Boots ribbon, a coherent curved chain threading through the void's interior. Both the 2MASS and SDSS datasets confirm the void's extent and the anomalous interior arrangement. The problem is not simply that the void is too large for the model. The problem is that it contains structure. Not an empty hole, not a random scatter. A shaped void with an interior chain that also lacks a standard explanation, forming something with a geometry inside a space that should not exist at its current size. What produced a coherent emptiness 330 million light-years across in a universe 13.8 billion years old? Are the 60 interior galaxies remnants of matter that failed to evacuate, or a new population condensing from material the void itself is generating? Why does the interior arrangement form a loop rather than a random scatter? Is the Boots ribbon a clue to the void's formation mechanism, or a coincidence with no explanatory weight? And if voids this size cannot form through standard processes, what process made this one? The Boots void sits and grows, and the galaxies inside it trace a chain nobody has a satisfying explanation for. What we found next wasn't static at all. It was pulling everything in one direction, towards something we have never been able to see. Number 3. The dark flow signal. The year is 2008. You're a cosmologist at NASA's Goddard Space Flight Center in Greenbelt, Maryland. The building is government functional drop ceilings, fluorescent panels, HVAC hum, the particular institutional quiet of a facility designed for documents and data rather than conversation. The work on your screen has taken years. You've been analyzing a specific kind of distortion in the cosmic microwave background, the Sunyaev-Zeldovich effect. A slight shift in the background radiation spectrum when CMB photons pass through the hot gas of galaxy clusters. The shift encodes each cluster's velocity relative to the CMB rest frame, a few microkelvins, measured across 1,000 separate objects. The velocities, according to every standard model prediction, should be random. They are not. Alexander Kashlinsky worked with Autrio Barandella, Kochevsky, and Ebeling. Their results appeared in the Astrophysical Journal Letters in 2008 paper, APJ 6, 86, L 49. The analysis covered approximately 1,000 galaxy clusters spread across a volume 6 billion light-years in diameter. Over a volume this large, individual cluster peculiar velocities should average out. Statistical cancellation is a basic prediction of the homogeneous, isotropic universe that lambda CDM describes. Instead, all 1,000 clusters were drifting coherently in the same direction, at approximately 600 to 1,000 kilometers per second, between roughly 1.3 and 2.2 million miles per hour. Not randomly scattered, not partially correlated. All of them drifting the same direction at the same time. Kashlinsky named it dark flow. The direction of the drift pointed consistently toward a region of sky in the direction of the constellations Centaurus and Vela. What lies in that direction, beyond the observable universe, beyond the cosmic horizon approximately 46 billion light-years away, is by definition unobservable. Kashlinsky's interpretation was specific. Something with a mass comparable to a significant fraction of the observable universe exists beyond the cosmic horizon, and its gravitational influence is detectable in the coordinated motion of 1,000 clusters on our side of that boundary. Here's where it gets strange. In 2013, the Planck satellite team published a null result paper, Planck collaboration, Ade et al., A and A, 561, A, 97. They could not confirm the dark flow signal. Kashlinsky responded that the Planck analysis had excluded the specific galaxy cluster catalog required to detect it. In 2015, he reran the analysis using Planck's own data, directly paper APJ letters 804, L40, and reported the dark flow signal intact at 99.5% statistical confidence. The Planck team maintained their null result. Both papers remain published. Neither has been corrected or retracted. The disagreement between two independent analyses of overlapping datasets by credentialed teams using legitimate methods has not been formally resolved. The source that Kashlinsky's data implicates cannot be observed, cannot be measured directly, and cannot be confirmed or refuted through any instrument we currently possess or could build. The signal, if real, is the gravitational shadow of something outside the boundary of everything we can ever see. What is the mass required to produce a coordinated drift across a 6 billion light-year volume? Is the Planck null result a methodological difference or a genuine contradiction? Can two separate analyses of overlapping datasets produce incompatible results through legitimate methods? And what does it mean for cosmological modeling if a gravitational signal from beyond the observable universe is real and measurable? Kashlinsky's clusters are all drifting in the same direction, towards something in the dark. But there's a different kind of signal embedded in the oldest light in the universe that suggests the dark itself may have a shape. Number 4. The CMB cold spot. The year is 2015. You're a researcher at the California Institute of Technology in Pasadena. The work on your screen is calibration, methodical, unglamorous, necessary. You're subtracting the Milky Way's foreground radio and infrared emissions from the Planck satellite's full sky map of the cosmic microwave background, isolating the primordial signal underneath. The Pasadena light outside is bright and indifferent. The room is climate-controlled. The CMB is the thermal remnant of the universe, as it existed 380,000 years after the Big Bang, a near-uniform map of the earliest recoverable light, spread across the entire sky at a temperature of approximately 2.7 Kelvin. The process of foreground removal fills hours. You do it carefully. When the subtraction is correct, what remains is signal. When you examine the residual, there is a patch. It is not noise. You know what noise looks like. The cold spot was first identified in WMAP satellite data in 2004 Vielva et al., the Astrophysical Journal, 609-22. It sits in the direction of the constellation Eridanus. It is approximately 1.8 billion light-years across. It is 70 microkelvins cooler than the average CMB temperature. The CMB itself fluctuates by only roughly 100 microkelvins across the entire sky, meaning this single region consumes the majority of the full thermal variation range. Under standard lambda CDM statistics, the probability of generating this feature by chance is approximately 1 in 50,000, per Drake et al., 2017. Monthly notices of the Royal Astronomical Society. Rangaram Cherry's 2015 analysis, published in the Astrophysical Journal at paper 805-2, found that the density perturbations and photon distribution in the residual signal were consistent with theoretical predictions for a bubble collision between our universe and an adjacent one, the signature expected under eternal. inflation models, where separate bubble universes nucleate and occasionally interact. The conventional explanation is the Eridanus supervoid, a genuine large-scale underdensity at redshift z, approximately 0.3, identified along the line of sight to the cold spot. The proposed mechanism is the integrated Sachs-Wolf effect. Photons passing through an expanding underdensity lose energy, producing a temperature deficit. Finetti et al. In 2016, and Marcosine Caballero et al. In 2019, both modeled the supervoid's contribution quantitatively. Both found the same result. The supervoid accounts for approximately 10 to 20% of the observed temperature deficit. The remaining 80 to 90% has no conventional explanation. Here's where it gets strange. Laura Mersini Houghton, a theoretical physicist at the University of North Carolina, predicted prior to the cold spot's full statistical characterization that quantum entanglement between our universe and a neighboring universe during the inflationary epoch would produce exactly this type of cold patch in the CMB. The prediction preceded the anomaly's complete characterization. The supervoid explanation, the best available conventional account, falls 80 to 90% short of explaining the observed deficit. The best surviving peer-reviewed explanation for the remainder is a parallel universe boundary collision. That sentence appears in a physics paper. Why does the Eridanus supervoid account for only a fraction of the cold spot's temperature deficit? What physical mechanism produces the remaining 70 microkelvin signature? Is the Cherry analysis identifying signal or residual foreground contamination? Why did Mersini Houghton's prediction match the anomaly's characteristics before the anomaly was fully measured? And if the cold spot is a boundary scar, what does that boundary separate us from? The cold spot sits in the CMB, radiating the wrong temperature, explained by at most 20% of the mechanism that should explain it. Whatever it is, it's passive. It just sits there. What comes next is not passive. What comes next is pulling us at 1.4 million miles per hour. Number 5. The Great Attractor. The year is 1986. You're a radio astronomer at Parkes Observatory in New South Wales, Australia. The dish behind the building is 210 feet across from the control room. It becomes background, a white bowl tilted toward the Southern Cross. The night air at Parkes is still in a way that high-altitude northern observatories are not, warm near the ground, carrying the dry grass smell of the Lachlan Valley pastureland, spreading in every direction around the facility. You've been part of a 7-person collaboration for years, compiling the most precise peculiar velocity map of the nearby universe assembled to that point. Peculiar velocities are the component of a galaxy's motion that cannot be attributed to the universe's general expansion, the gravitational signature of local structure. The survey has covered every galaxy within 250 million light-years. The result, when the vectors are plotted, is unambiguous. Everything in the survey, including the Milky Way, is moving in the same direction. The map did not predict this. The team is known informally as the Seven Samurai. Alan Dressler, David Burstein, Roger Davies, Donald Lyndon Bell, Roberto Turlevich, Gary Wegner, and Sandra Faber. Their results appeared in the Astrophysical Journal Supplement in 1987 paper APJ S65 539. What the peculiar velocities implied was a gravitational source of extraordinary scale positioned 150 to 250 million light-years away. Estimated mass, approximately 10 to the 16th solar masses, roughly 100,000 Milky Way equivalents. The Milky Way, the local group, and the entire Virgo supercluster are all being drawn toward this concentration at approximately 600 kilometers per second, roughly 1.4 million miles per hour. The source had no visible counterpart in optical surveys. The Seven Samurai named it the Great Attractor. The problem they encountered immediately was geometric. The Great Attractor's location corresponds to the zone of avoidance, the band of sky where the Milky Way's own disk, with its gas, dust, and stellar density, blocks optical observation of whatever lies behind it. Approximately 20% of the full sky falls within this zone. X-ray surveys using the Rosat satellite and radio surveys using the Parkes multibeam system identified a probable mass concentration, the Norma cluster, Abel 3627, as the likely anchor. Kron-Korteweg et al. Published this identification in Nature in 1996. Brent Tully, Helene Courtois, Yehuda Hoffman, and Daniel Pomerede published the Laniakea supercluster map in Nature in 2014 paper 5.13.71. The Great Attractor anchors a supercluster 520 million light-years across, containing approximately 100,000 galaxies, with a combined mass of roughly 10 to the 17th solar masses. Here's where it gets strange. The center cannot be directly observed. Roughly 20% of the full sky remains significantly obscured by the Milky Way's own disk as of 2024. Every mass estimate for the Great Attractor's core is derived by modeling surrounding structure and inferring what must be at the center to produce the observed velocity field. Not confirmed by imaging. Not constrained by direct observation. Inferred because our own galaxy is standing in the way. We identified the object pulling us decades ago. We mapped the supercluster it anchors. We named it. We still cannot see it. What is the precise mass of the structure at the zone of avoidance's center? Is Abel 3627 the primary concentration, or does the zone conceal a more massive object behind it? Does the full Laniakea velocity field account for the total peculiar velocity of the local group, or is there a residual unexplained component? And what would a direct observation of the Great Attractor's core reveal that 4 decades of multi-wavelength inference cannot? The Great Attractor is invisible, but at least it's located. The next structure was visible in publicly available data the entire time, and a graduate student found it, and the field decided not to look. Number 6. The Giant Arc. The year is 2020. You're a PhD student at the University of Central Lancashire in Preston, England. The office is shared fluorescent overhead, tea going cold beside the keyboard, the institutional smell of carpet and printer toner that accumulates in every underfunded research building. Your screen shows the DR16 Quasar catalog from the Sloan Digital Sky Survey, a public dataset, available to any researcher with a computer and a login, sitting open on a server that hundreds of other researchers have accessed. You're running a clustering analysis on quasar positions at a particular redshift, testing for large-scale correlations in the matter distribution. Quasars are bright enough to be detected across billions of light-years. Their positions trace the skeleton of structure at cosmological distances. You are not looking for the largest known curved structure in the observable universe. You find it anyway. Alexia Lopez and her supervisor Roger Clowes published their results in monthly notices of the Royal Astronomical Society in 2022, paper 516. 2, pages 1557 to 1572. The finding was first presented publicly at the 238th meeting of the American Astronomical Society in June 2021. What the quasar clustering analysis revealed was a structure 3.3 billion light-years in length, curved, coherent, and composed of galaxies, quasar groups, and galaxy clusters arranged along a single arc, spanning an enormous fraction of the observable sky. It existed at a point when the universe was approximately 6 billion years old, at a distance of approximately 9.2 billion light-years. It is the second largest known structure in the observable universe, smaller only than the Hercules-Corona Borealis Great Wall from Section 1. Both violate the same principle. Both remain unconfirmed by independent observation. The cosmological principle, again, is the relevant constraint. Maximum coherent structure under the Standard Model, approximately 1.2 billion light-years. The giant arc is 3.3 billion light-years long. That is a violation by a factor of 2.75. Lopez and Clowes applied the Rayleigh statistic and bootstrap analysis to eliminate systematic effects in the SDSS survey geometry. The statistical significance of the detection came in at 4.3 sigma. In observational astrophysics, 3 sigma constitutes a significant finding. 5 sigma is the confirmed discovery standard. The giant arc sits between those thresholds, above the floor, below the ceiling. Here's where it gets strange. The detection required no new telescope time, no proprietary instrument, no mission-specific dataset, no observational campaign costing millions of dollars. The entire detection was performed on publicly available data that had been accessible to any researcher for years before Lopez ran her analysis. Verification using a separate instrument or independent catalog is straightforward, in principle. Acquire the same region of sky with a different survey. Test whether the clustering holds. As of 2024, no independent observational campaign using a separate instrument or catalog has been funded or completed, not submitted and rejected, not under review, not organized. A 4.3 sigma result for the second largest known structure in the observable universe, found with public data by a PhD student, is waiting for confirmation that has not been arranged. Why has no independent survey been funded to confirm or refute a 4.3 sigma violation of the cosmological principle? Does the giant arc's curvature represent a coherent three-dimensional structure or a projection effect? If confirmed, what early universe process produced a curved, coherent feature 3.3 billion light-years long? How many comparable structures might exist in public catalogs, undetected, waiting for the right analysis? And what does the coexistence of both the Great Wall and the giant arc, two structures violating the same principle at separate redshifts, imply about that principle's validity? Lopez found the giant arc by looking outward, at a distance of 9 billion light-years. What's more disorienting is what we found when we looked inward at the place where we ourselves are sitting. Number 7. The KBC Void. The year is 2012. You're a cosmologist at the University of Hawaii at Manoa in Honolulu, running a galaxy redshift survey that spans approximately 300 megaparsecs, roughly 980 million light-years, in every direction from where you're sitting. Outside, the campus sits at sea level on the leeward side of the Ko'olau Range, trade winds cutting down the Manoa Valley, the air warm and humid in the specific way of a tropical island at elevation. Inside, you're looking at density measurements. The survey is designed to measure local matter density, how much mass per unit volume exists in the region immediately surrounding us, compared to the cosmic average. The cosmological principle predicts that local density should converge toward the cosmic mean at large enough scales. You are sampling a region large enough that convergence should be visible. The density is low. Significantly, consistently, persistently low. The convergence is not coming. Ryan Keenan, Amy Barger, and Lennox Cowie published their results in the Astrophysical Journal in 2013 paper APJ 775-62. What the survey found was that we are positioned near the center of a spheroidal underdensity approximately 2 billion light-years across. The local matter density within this region runs approximately 20 to 30% below the cosmic mean. This is not a statistical fluctuation. It is a coherent, measured deficit in the density of matter across the largest volume of space our local surveys can effectively characterize. We are sitting in a hole. The Hubble tension is the most statistically severe, unresolved problem in modern cosmology. Local distance ladder measurements using Cepheid variable stars and Type Ia supernovae, most precisely compiled by Adam Rees and collaborators in 2019, return a Hubble constant of approximately 73 kilometers per second per megaparsec. CMB-derived measurements from the Planck collaboration return approximately 67.4 kilometers per second per megaparsec. Both measurements use independent methods and independent datasets. Both are highly refined. The discrepancy between them has grown as measurement precision has improved and now stands at approximately 5 sigma. 5 sigma. Unresolved. Here's where it gets strange. The KBC void provides a direct physical mechanism for the entire discrepancy. Inside a significant underdensity, the local expansion rate is slightly faster than the cosmic mean matter evacuates the void's interior outward towards surrounding denser shells. An observer near the center of this expanding underdensity would measure a locally elevated Hubble constant, precisely matching the offset between local and CMB-derived values. Hochheit and Barger published a formal, quantitative analysis in the Astrophysical Journal in 2018 paper 854-46, demonstrating that the KBC void's measured parameters can account for the full Hubble tension without invoking new physics beyond the standard model. Every local measurement of the Hubble constant made over the past 40 years may be systematically biased by the same cause, not a calibration error in the instruments, not a statistical fluke in the data. A position error, we are in the wrong place to measure the cosmic average, and we have been measuring from that wrong place for 4 decades without knowing it was wrong. Is the KBC void deep enough to fully account for the Hubble tension, or is the EBOS survey's less pronounced underdensity measurement more accurate? If our local measurements are biased by position, Which cosmological measurements constitute reliable baselines? What does it mean for 40 years of precision cosmology if the reference frame was compromised from the start? And if the Hubble tension is a position artifact, what other systematic errors are embedded in our measurements for the same reason? We live inside a void, drifting outward with the expanding underdensity. But it's not only the void pushing us. Something specific, in a specific direction, has been doing the other half of the work. Number 8. The dipole repeller. The year is 2016. You're a cosmologist at the Hebrew University of Jerusalem. The office looks out over the Judean hills when the window is unobstructed and the afternoon haze hasn't settled in. The work on your screen has taken years. You've been reconstructing the three-dimensional peculiar velocity field of the local universe using data from the cosmic flows, 2 catalog peculiar velocity measurements for 8,000 galaxies, the most comprehensive such dataset assembled to that point. The reconstruction requires the Wiener filter, a statistical method that takes individual galaxy drift velocities and extrapolates the underlying gravitational field responsible for those motions. The output is a map. On one side of the map, there is a gravitational attractor, the Great Attractor, where it has been since the Seven Samurai identified it in the 1980s. Then you look at the other side of the map. The galaxies on that side are not falling inward. They are running away from something. Yehuda Hoffman worked with Daniel Pomerade, Brent Tooley, and Helene Courtois. Their paper appeared in Nature Astronomy in January 2017, Volume 1, article number 0036. What the velocity field reconstruction showed on the far side of the sky from the Great Attractor was a systematic pattern, galaxies flowing outward, away from a central region, as if being expelled. The inference was a large underdensity, approximately 600 million light-years away, in the direction of Gemini. In the physics of large-scale structure, a void repels surrounding matter, the same way a gravitational attractor draws it. Matter flows from low-density regions toward high-density ones. The outward flow is not expansion, it is gravitational evacuation. Not a mass, not a visible object, an absence, defined by what flows away from it. Our peculiar velocity relative to the CMB rest frame has been measured precisely. Kogut et al. Published the figure in 1993 in the Astrophysical Journal, paper 419-1. Approximately 627 plus or minus 22 kilometers per second, approximately 1.4 million miles per hour. Before the dipole repeller was identified, models incorporating the known large-scale structure, including the Great Attractor and Laniakea, could account for approximately 50% of this peculiar velocity. The other half was unexplained. Measured, confirmed, repeatable, and without an identified cause for roughly 30 years. The dipole repeller accounts for the other half. With both forces identified, the full peculiar velocity of the local group is now accounted for. We are between them. Here's where it gets strange. The structure responsible for half of our total velocity through space, half of 627 kilometers per second, measured and confirmed for 3 decades, was only identified in 2017. For approximately 30 years, from the time the peculiar velocity was first precisely measured until Hoffman's paper appeared in Nature Astronomy, we were being pushed by something we had not detected. The dipole repeller cannot be directly imaged. It is defined by a systematic absence of galaxies, confirmed through analysis of redshift space distortions in surrounding large-scale structure. Not a visible mass. Not a detectable emission. An inferred absence defined, measured, and confirmed as the force responsible for half of our motion through space. For what mechanism has a structure 600 million light-years away been pushing the local group across the full history of observable cosmology? Why was the velocity field analysis that revealed it not performed until 2016? What other significant features of the local velocity field remain unidentified in current catalogs? And if both forces driving our motion through space were identified only within the last few decades, how confident are we that the local gravitational environment is now fully characterized? We've mapped what pulls us and what pushes us. None of it is visible. The scaffold that holds 2 trillion galaxies in position is made of something no instrument has ever directly detected. Number 9. The cosmic web. The year is 2019. You're a computational astrophysicist at the University of Bologna. The simulation running on your workstation processes a cubic volume 300 megaparsecs on a side roughly 980 million light-years of simulated space. The machine runs overnight. Bologna in the early morning is quiet in the way of old university towns. Cobblestone outside, the smell of espresso from the bar downstairs, pigeons on the portico. You are watching a universe assemble itself on a screen. In the morning, the visualization resolves. Filaments of dark matter threading between nodes, flat sheets at the intersections of density flows, enormous voids where matter is absent, compact concentrations at the nodes where filaments converge. Every simulated galaxy appears at one of those nodes, or along one of those threads. This is expected. The web structure is one of the most well-confirmed predictions of the Lambda CDM model. Then you load a second dataset, a high-resolution scan of a section of the human cerebellum. You run the same structural analysis on both datasets. You get the same answer. The cosmic web is not a metaphor. It is the literal architecture of the observable universe. Approximately 27% of the universe's total energy density consists of dark matter, matter that interacts gravitationally but emits no detectable electromagnetic radiation. Ordinary baryonic matter, everything made of atoms, including every galaxy we have ever observed, constitutes approximately 5% of the total energy density. The filaments of the cosmic web are composed primarily of dark matter, with ordinary matter tracing the gravitational skeleton, Consolis et al. Published an estimate in 2016, the Astrophysical Journal 83083, that the observable universe contains approximately 2 trillion galaxies. Every one of them is positioned at a node or along a filament of this dark matter web. Franco Vazza and Alberto Folletti of the University of Insubria published their comparison study in Frontiers in Physics in 2020, paper 8, 525, 731. They applied power spectral analysis, cross-correlation functions, and structural complexity metrics to both a simulated cosmic web slice and a high-resolution scan of the human cerebellum. The cerebellum contains roughly 69 billion neurons. The observable universe contains roughly 2 trillion galaxies. The power spectra that characterize their spatial distribution and structural complexity produce the same measurement, not approximately similar, not visually suggestive, statistically indistinguishable across multiple independent metrics. The cosmic web has not been fully mapped. The dark matter component has never been directly imaged. It is inferred from gravitational effects on the matter we can observe. The Hyper-Suprime-Cam Subaru Strategic Program, reported by Hikage et al. In 2019, produced the most detailed direct map of dark matter distribution to date through weak gravitational lensing. Cantalupo et al. In Nature in 2014 paper 506-63 achieved the first direct detection of a cosmic web filament in emission, a single hydrogen gas filament extending more than 2 million light-years. One filament, detected once. The estimated hundreds of billions of filaments threading the rest of the observable universe are inferred, not seen. Here's where it gets strange. Vazza and Folletti did not find a metaphor. They ran the same mathematical analysis on both systems and found the same answer. One system is the observable universe, spanning 93 billion light-years, assembled over 13.8 billion years by gravitational physics acting on quantum fluctuations in the first fraction of a second after the Big Bang. The other is a section of tissue inside a human skull. The structural signal is the same measurement. What physical process produces identical structural signatures at scales separated by a factor of roughly 10 to the 27th? Is the similarity a deep constraint imposed by information processing architecture, or an accident of the same mathematical forms appearing in unrelated systems? Why has only one cosmic web filament ever been detected in direct emission? How many of the 2 trillion galaxies in the observable universe remain uncatalogued? And what is inside the filaments we have never directly seen? The web holds 2 trillion galaxies in position through filaments we've detected once, and occasionally, 2 of the nodes it connects collide at velocities and masses the standard model says should be impossible. Number 10. El Gordo. The year is 2011. You're a cosmologist at Rutgers University in New Brunswick, New Jersey, examining data from the Atacama Cosmology Telescope in the Atacama Desert of Chile. The Atacama is the driest non-polar desert on Earth. The instrument sits at 17,000 feet elevation, above most of the atmosphere's water vapor, in air so thin and clear that the sky at night is almost three-dimensional. The telescope maps the cosmic microwave background using the Sunyaev-Zeldovich effect. Galaxy clusters appear as shadows against the microwave background, their hot intracluster gas imprinting a characteristic spectral distortion on CMB photons passing through. The software has flagged an object in the direction of the constellation Phoenix. The shadow is large, unusually large. You run the mass calculation. You run it again. You run it a third time. The number does not change. Felipe Menanto and collaborators published their results in the Astrophysical Journal in 2012, paper 748-7. The object is a merging system of two galaxy clusters that have already passed through each other, their components now separating on the far side of a collision, occurring when the universe was approximately 6.5 billion years old. Combined mass: approximately 2 to 3 quadrillion solar masses, 2 to 3 times 10 to the 15th solar masses confirmed through Hubble Space Telescope weak gravitational lensing by G et al. In 2014. Paper AppJ 785-20. Collision velocity: approximately 2,000 kilometers per second, roughly 4.5 million miles per hour, at closest approach, with a total system velocity between 4,000 and 5,000 kilometers per second, 9 to 11 million miles per hour. Chandra X-ray observatory imaging shows the characteristic bullet morphology. The hot intracluster gas was stripped by ram pressure during the collision and now lags behind the dark matter halos, which pass through each other nearly unimpeded. The collision occurred. The geometry is confirmed. The numbers are confirmed. The nickname is El Gordo, Spanish for the fat one. Menanto and collaborators cited the tension with the standard model explicitly in their 2012 paper, under lambda CDM. The probability of a galaxy cluster of this mass existing at redshift z equals 0.87 is approximately 3.3 times 10 to the negative 10th. G et al. In 2014, identified three possible explanations. 1. Primordial density fluctuations were larger than lambda CDM predicts, meaning the initial conditions written into the standard model are wrong. 2. Dark energy behaved differently in the early universe, allowing faster structure formation than the current model permits. 3. The standard model requires revision at a fundamental level. As of 2024, El Gordo remains the most massive known merging cluster system at its redshift. No consensus standard model explanation for its formation has been published. Here's where it gets strange. The probability is 3.3 times 10 to the negative 10th. Under the current model, this object should not exist. It does exist. It has a confirmed mass, a confirmed velocity, a confirmed collision geometry, a nickname, and 2 confirmed papers. The model didn't predict it. The model quantified how unlikely it was. The object formed anyway. How did a structure of this mass form in a universe that was only 6.5 billion years old at the time of its collision? Does the bullet morphology at this redshift and mass indicate a universal mechanism, or is El Gordo a singular event? If primordial density fluctuations were larger than predicted, what other structures formed earlier and more massively than we currently expect? And if the standard model cannot account for a probability of 3.3 times 10 to the negative 10th, at what point does a collection of anomalies constitute a refutation? Every structure in this video, 10 entries, spanning from 330 million to 10 billion light-years, represents a measurement that falls outside the parameters of the model used to describe the universe we live in. The anomalies are not isolated. They are distributed across every scale and every distance at which we have made sufficiently precise observations. Subscribe if these structures are worth tracking, like if any one of them landed, and leave a comment telling us where you're watching from: a city, a country, whatever part of this particular void you happen to occupy. The model said El Gordo shouldn't exist at redshift 0.87. The model also said the Great Wall was too large to be coherent. The Boots void took longer than the universe's age to form. The cold spot was a statistical artifact, and the dipole repeller didn't exist until someone measured it in 2017. The universe is not consulting the model.